All right, let's get started, everyone. How's everyone doing? Good. Fabulous. Awesome. Better now than when I asked. All right. So today we're going to be talking about something called two pointers and something called linked lists. I like two pointers. I hate linked lists. I think you'll when you do the poems, you'll feel the same thing. So I'd like to first review what we went over last time, since I know it's been 2 weeks. It's probably left your brain by now. So first thing that we covered last time was big O complexity. Big O complexity was the measure of how efficient a code is. As competitive programmers, it's our job to make this as small as possible. Big O is based on the input size. So for example, if the input is a string then a big O would be based off of the size of that string. Or if an input was, say, a number, like an integer n, then a big O would be based off that number. Now, when we're doing big O complexity, we only care about the highest exponent. So for example, if we do n squared plus n plus 1 operations, we only care about the n squared. Nothing else is included. So just going, and then, yep. So now the next thing I went over last time was sets. Now sets are data structure that are really useful for its O(1) insert, deletion, and find operations. So that means that you can put something in the set, remove something from the set, and see if something is contained within the set in constant time. So you could have it in a for loop and check if something is contained within the set, and that would not change your time complexity. So you can, it's really useful for keeping track of what you've seen before. So for example, this has duplicate number code right here. Without a set, the only way to do it really is to do it in over n squared time. We have to check every pair of elements and see if they're equal to each other. And if they're equal, then we found the duplicate. But with a set, we can keep track of the numbers that we've seen before. And for each number, see if we've seen that number before. And then after we check that, add it to the numbers that we've seen before. So basically, 1, 2, 3, 1. We haven't seen 1 before, a set is empty. Then we add it to the set. We haven't seen 2 before in a set. We add it to the set. We haven't seen 3 before in a set. We add it to the set. We have seen 1 before in a set, so we return true. That makes sense? All right. Now, maps. Maps are basically like sets. They except they have a key that corresponds to a value. So just like sets, they have O(1) insert, removal, and contains functions. But like I mentioned before, each one of these would then have a corresponding value. So say, for example, I wanted to keep track of the index of each number. So then I could, let's do count of each number. So then I could have a map. So I first see this 1. I initialize it with, I've seen it 1 time. I see this 2, I've seen it 1 time. 3, I've seen it 1 time. The second 1, I already see that I've seen it 1 time, so I could increment this value and send it to 2. So maps, like sets, except we have a corresponding value. This is really useful for counting occurrences, like I just did, keeping track of element indices in an array. For example, if I wanted to say, oh, this 1 is at index 0, this 3 is at index 2, etc., then that's what maps are really useful for. And also, if you've done dynamic programming before, you know that they're really good for caching results. But we won't get into that right now. So let's start out with 2 pointers. So let's first think about how we go through an array typically. With an array, we typically have a for loop. We typically have I equals 0, I is less than the length of the array, array.length, and then I plus plus. And this, let's call this a pointer. So then when we do array of I, we're sort of looking in our array, and we're moving this pointer right by 1 every single time as this I increments. So with 2 pointers, instead of only utilizing 1 pointer to traverse through an array, 2 or more pointers are used. So it could look something like this. Maybe instead of just having 1 pointer, you could have 2, or we move both at the same time. That sort of theoretically makes sense to everyone? The idea of 2 pointers versus 1 pointer. So 2 pointers can be used to do a lot of different things. For example, you might recognize this question from the coding challenge that I had, that we had at a tabling event. But let's say we're given a string and we want to check whether it's a palindrome. So it's the same forwards and backwards. So something like A, B, C, B, A. If you flip this, it's the same. It's the same. So A, B, C, B, A backwards is A, B, C, B, A. So the way to do it with 1 pointer is to go through each element in a string, and then find the corresponding character that we have to check it with. So for this first A, we have to calculate, we have to access the last A and check if these 2 A's are equal. And if they're not equal, then it's not a palindrome. For example, like A, B, C, B, B, this A and this B are not equal. So we can say that it's not a palindrome. And then we just continue on, we check the next pair, and then we check the next pair, etc. But you sort of see right here, the calculation that we do to get this corresponding A with this corresponding B is not great. It's s.length minus 1 minus I. So one thing about 2 pointers is that you can clean up this ugly code. So for instead of having just like having a for loop and then calculating the corresponding opposite side of the string using this formula, we can simply have 2 pointers. We can have a left pointer and a right pointer. So where's the so say for like let's do a long string. We start our left pointer here and a right pointer here at s.length minus 1. We then check to see, we then access the character at the left pointer and the character at the right pointer. So that's stored in current and reverse. If the current is not equal to the reverse, then we return false. In this case, they're equal, so we just continue on. And then here's the magic part. We move the left pointer right one, so L plus plus, and move the right pointer left one, right minus minus. So I think that this code is much cleaner than this code. And that is because of 2 reasons. One, we don't have this ugly s.length minus I minus 1, or minus I minus 1, yeah. And it's very clear what we're doing with our different pointers. We're moving the left one right and the right one left. Any questions about that? Yes.
Is it possible for us to just do like that's not playing divided by 2, like the string is already?
That is a very good point. So so yeah, we could do well, left is less than s.length by 2. I think there might be a +1 that you have to add there. But we could also just say, well, left is less than right. And that means that it'll stop when the left and the right hit the same pair. So yeah, as she mentioned, with this, we can also use a true pointers to add a stopping condition when the two pointers intersect. So that's another thing about two pointers, is that you can then compare them very easily. So here we had the two pointers go in opposite directions. We had the left pointer go right and the right pointer go left and sort of go inwards. But the two pointers can go in the same direction as well. For example, and the two pointers don't have to be updated simultaneously. So here we in this code, we updated them at the same time, but that doesn't have to be the case. So this upcoming problem is, let's say that we're given a list like 1, 2, 4, 5, 3, 6. Well, we want to find the shortest sublist with so that means the shortest sublist is like take a contiguous block of elements. So for example, it could be 2 to 5, or it could be this 4 to 6, or this 5 to 3, or this like 1 to 4, but you can't do like a 1 and 6. That wouldn't be a sublist. That wouldn't be a continuous. So we want to find the longest continuous sublist where all the numbers are greater, where the sum of the numbers is greater than the target sum. So let me add some negatives here. So let's say that we have a -10 and then wait, sorry, I got that backwards. This would be the problem of where we want to find the shortest sublist of where the numbers that we add up reach the target. So say for example, our target was 7. Then this 3 to 5 is of length 2, and it reaches its sum is 8, and that's greater than 7. That makes sense. Does anyone want me to explain it again? Yeah, greater than or equal to 7. Can you say that again? Yep. So what we want to do in this problem is find the shortest continuous sublist of elements in this array, where the sum of those elements is greater than or equal to some value k. In this case, let's say 7. So let me switch it up a little bit. Let's say like this. In this case, it would be these two. It's just length 2, and it's greater than or equal to 7. So how do we do this? The naive way would be to test every single sublist and see if it, first of all, if it sums up to greater than or equal to 7, and if so, what the length of that is, and then update the minimum length that we seem to put. And this is something called brute force. So we could try every single sublist. Start with the 1, start with that. Test every one of those, and then start with the 2, start every one of those, etc. That is too slow. That would be over n squared time. But we could do better than that with 2 pointers. So now this is a hard one, so it's fine if you don't get it. But I just wanted to highlight the power that 2 pointers have. So instead, we could use the two pointers to do the following. We initialize our left pointer at the beginning, our right pointer at the beginning, and as long as and we expand our right pointer until we reach the point of where the sum is greater than or equal to 7. So in this case, that would not be until we reach here, where it's 1, 3, 4, 9. So now we know that this is the shortest sublist that we've seen so far, where the sum is greater than or equal to 7. That makes sense so far? Now, if we move a right pointer right one, we know that this won't be efficient because we already found one that's shorter, right? There's no point in going further. Instead, what we do is we move our other pointer. So we move our left pointer, and we start to shrink this window. Say, okay, we went as right as possible. Now let's try to shrink the selection that we have. So we now have this, and we can subtract this 1 that our left pointer was pointing at, and the sum would equal 8. So just by doing that, we found the shortest sublist. That makes sense, everyone, so far? And we continue doing that until we reach here. In this case, a sum is 6. So now we say, okay, we started removing elements, now we need some more elements. So we expand the right again. And then we add this 3. So now we're back to 9 and say, okay, that's a length 3. And then we do the same process of where we move the left pointer, we subtract this 1, and oh, look, we found a sublist of length 2. So I won't go super into the implementation of it, but that's a technique called sliding window. And I just wanted to highlight that 2 pointers can be used to do lots of different things. But yeah, there won't be any problems like that in the set that we have today. But if you're definitely interested, I'd look at the code more deeply and see if you could follow through what I sort of did there on your own. Any questions? All right, so let me introduce you guys to something called linked lists. How many of you have used a linked list before? Okay, good amount. How many of you have heard about linked lists before? Okay, same amount. So what is a linked list? So we have arrays and we have linked lists. The two are very similar, except linked lists are 10 times more annoying. What the heck? So with an array is stored as like a block in memory. So you have your elements. And the good thing about an array is that you can access any element that you want in constant time. So you could say, I want the 6th element, and you can do that immediately. I want the 3rd element, you can do that immediately. However, the problem with arrays is that you can't resize that, quote unquote. Once you say, I want this block of memory, you can't suddenly say, oh, can I just have one more? That isn't really possible. But what it is possible with is with a linked list. A linked list, you can think of it as sort of nodes. Let's call these nodes and pointers. So let's look at the code for it. So you can see that each node contains a value. So in this case, it would be, let's say 1, corresponding with this one. But it also contains another linked list node. And this is the next node in the linked list. So we have 1, and the next node would be a node with 3. And we have 3, and the 3 will contain, will reference the next node, which will be a node with 4, etc., etc. That makes sense? Now, There's some distinction with the fact that the next node is not like a direct reference, but instead a pointer, but I won't get into that. It's not important for the concept of understanding linked lists. But the thing about linked lists is that we can very easily add something onto the end of the linked list. Like with the array, this is like a constant block of memory, and we can't just add one on more. Or with the linked list, we could just say, oh, this next thing at the last element, let's just point that to another node. So that's what linked lists are used for in actual code. But when we're doing competitive coding, linked lists are just there to get in the way, there to make your life hard. So, any questions about anything I'm talking about so far? All right, let's take a look at some code. So this is an algorithm that will print a linked list. So the way that we do things is again with pointers. So the first thing that I'll do is I'll say, let's have this pointer called cur, and I'm going to point that at the very first element in the linked list. Whenever you're given a problem with corresponding to a linked list, it'll probably always give you the head of the linked list. So the very first element in the linked list. So I'm going to say that cur is looking at the head of the linked list. And that's what this line of code, line 13, is doing. So in order to print each node in this linked list, it's not as simple as just like a for loop and then we print each array of I. We can't do that for all linked lists since these aren't arrays. So instead, we have to do the following algorithm. So ignore this cur does not equal null for now. Let's just say that this is while true. So while true, so this is for infinite loop. Let's print out the current node that we're looking at, its value. So first we print out 1, and then this arrow corresponds to the next. Then we set cur to be the next node. So we move a cur here. And that's what line 16 is doing. That makes sense? And then we repeat that process. We print out 3. This is now a cur is pointing at the node with 3 in it. And then we move a cur to the next pointer. We print out 4. And then let's say this was pointing at null. Then we move a cur to the next pointer. And then this is why we wanted to print out, why we wanted to have the cur does not equal null. When cur equals null, we've reached the end of the linked list. So there's no more elements in the linked list. So then we stop and exit the while. That makes sense, everyone? So here's another example. Same concept of where we have a cur, we iterate cur to the cur.next value, and then we have a cur does not equal null in the while loop. So we set here. In this case, we want to sum together the elements. So we have we initialize sum to be 0. So let's store the sum here. We point cur at the initial value. We add that value to the sum. Move on to the next one. Same process. We add it to the sum. We move on to the next one. We add it to the sum. And move on. And now it's null. So then we exit the while loop, and now we've added all the elements in the linked list. So you can sort of see it's similar to a for loop for an array, except it's a little bit wonky and it smells funny. So solving linked list problems. So there's a couple strategies. One is to use multiple pointers. For example, I just had one code run through, but it's often useful to have 2 pointers in a linked list. It's often useful to keep track of the previous pointer. And we'll see examples of that. Like the previous node that we looked at, what was that? Well, it could be that you move one node faster than the other. You move one pointer faster than the other. So for every time that the curve moves, you have another pointer that moves twice as fast through the linked list. And I'd also suggest that with linked lists, you create something called dummy nodes. I'll get into a little bit later, but dummy nodes are basically you make a fake node at the beginning, and this will just make your code plainer. And then finally, you walk through the algorithm on paper and whiteboard. I really suggest this because linked list problems are extremely implementation heavy, which means that there's a lot of places where you can code and go wrong. So it's really important that you, just like how I did with the sum and the print, you walk through it step by step on paper so that you know what's going on. So let's look at this insert into sorted linked list algorithm. So in this problem, we have a linked list where all the nodes are in ascending order. So something like 1, 3, 4, 5. Well, let's do like 7, 6. And then let's say that we're given a value. Let's say that we're given 5. We want to insert this into its correct spot in the linked list. So that what we should end up with is 1, 3, 5, 6, 7. Make sense? So how do we do that? Ignore the dummy for now. Let's just walk through it on the board first and then translate that into the actual code. So we're looking at this. We know that 5 is greater than 1, so we know that that's not where we have to insert it. We look at this 3. Oh, 5 is greater. We look at the 6. And all of a sudden we say, oh wait, this 6 is greater than the 5. We needed to insert the 5 right here. But the problem with is now that our pointer is at the 6, there's no way to get back to the 3. Does that make sense? Because there's no previous node in the list. We can only follow the arrows. We can only go next. There's nowhere to go pre. So what we do, we use the strategy of 2 pointers. Instead of just having 1 pointer, we have 2. So we have, can you guys see that? We have a prev and we have a curve. And then we do the same thing, except we move both at the same time. So we start up with like this, and we're looking for the point of where a curve is greater than or equal to the 5. That will be here. And now that we're storing the prev, then we can do, now we can say that the next element of prev is 5. And do this. Without these 2 pointers, it would have been possible. That makes sense? Now, there's one more issue. Let's say that the linked list is like this, and we want to implement, we want to add 5. In this case, a prev would be pointing to null, and a curve would be pointing at the 6. So we immediately say, okay, now prev, the next element of prev has to be the 5. But wait, prev is null. There's no way to set the next element of null to be 5. Now, you could do this through an if statement and just add some special code to handle this case. But the way that I like to do things is I like to add a dummy node. So like we're given this linked list. The first thing that I do is I add like a fake node at the beginning. Like I add a node with -1 at the value. That way, prev is always pointing at something. And then I can directly add 5 to the linked list. And then at the end, when they ask me to return the head of the linked list, I can just return the element after the dummy, the node after the dummy, and that will return the head, which is now 5. So that might be a lot to go through. Let's walk through the code just so that you get a gist of things. Is it not showing? Okay, so first thing that I do, I create a dummy linked list node. So that corresponds to creating the -1 here. This is the dummy. I set prev to be the dummy. And I set current to be the thing after the prev. So current is pointing at what was the head that was passed in. Now, while a current does not equal null, so we're going to continue until we hit the end of the list. If the val ever hits is greater than the current value, then we create a new linked list node with current as the next value. So for example, in this case, that would be we create a node and have what a current is pointing at as the next value. And we set that to be the next value of prev. So that corresponds with redrawing this arrow and putting it at that new node. And then of course, if we didn't, then we exit the while loop. But of course, if we didn't find it, the spot to insert there, then we move a current and a prev pointers to the next. We try that algorithm again. Does that make sense to everyone? All right. Awesome. I will not go into this one right now. I'll go into it a bit later. But yeah, that's basically it for my presentation. So a couple updates. We do have a homecoming, upcoming October 15th. Wait, no. Is that October? Yeah, October 15th. And then, so basically it's going to be a tabling opportunity. If you're interested, let me know. So I have to send whether or not the club's interested in going to that. And then I also want to see, would you guys be interested in going to a coding competition potentially? Yes? Yes?
Yeah.
Well, I'll have to see, but yeah.
Competing or spectating?
Competing, but it's not like high stakes. Okay. Yeah, so it seems there's some interest, so I'll look into it as I'll look into it and then see if there's any opportunities for us. All right, that's it for me. Thank you guys. No.